this video, I will show you why we get zero voltage switching on the primary side of the LLC. And this only occurs when Ix is not equal to 0 when we switch. So I will afterwards explain to you why it's like that. So first I want to show you the LLC converter. So you can see that we have two MOSFETs here, and the MOSFETs here are actually not ideal. So there's actually a capacitor in parallel with both of the MOSFETs. And this is very important for the zero voltage switching. So when we're looking at the zero voltage switching of the half bridge, we actually don't need to look at all of this mess as long as we know Ix. So now we just have the half bridge here, and you can see that we have two signals going into the MOSFET, which is one signal for each MOSFET, and VM1 is the voltage over the MOSFET with the signal 1, and the same for VM2, which is this voltage, basically Vx. So if we, for example, take this scenario here when S1 is on at the beginning and then S2 is off at the beginning, then the voltage over the MOSFET 1 would be equal to 0, as I drew here. And the voltage over S2 would be equal to the supply voltage. I didn't draw that, but we have, for example, VDC here. So VM2 would be equal to VDC. So now we have a dead time between S1 and S2. That would just mean that they don't switch simultaneously. We have a time between where both of the MOSFETs are off. But if we didn't have that time, this M2 here would switch when the voltage is equal to VDC. And that will result in a lot of losses, and we don't want to do that. So we just remove it. So now what happens when both of the MOSFETs are off in the dead time zone here? But now what happens when both of the MOSFETs are off? That is in the dead time here. So at the beginning, this one was closed. So the current was running like this, or going like that. And then this one switches off at 0 voltage, which means that there are no power losses, but the current needs to go somewhere. So it starts going through the capacitors, right? Goes through both of them, because the capacitance is equal in both of them, ideally. So now when there is a current in a capacitor, the voltage would start to change, because IC is equal to C multiplied by the change of voltage. So you can see that when IC is positive, there is a positive increase in the capacitor. The positive direction of a capacitor, the current in a capacitor, is this direction, which would mean that in this case, the current is positive, which means that the voltage will start to increase. So we know that the voltage just starts to increase until it reaches the maximum value. And it will be the opposite for this case, right? So the current is negative, it's going upwards. And the voltage will therefore start to reduce. So we can draw a reduction here. So you can see that when this MOSFET here turns on, the voltage is 0. So we have no power losses there as well. But now we just assume that this current here is non-zero. But why is it? And now I will show you exactly the waveform of the current and why it's not 0. So now I want to look at the resonant tank, which is this one. So we have a voltage Vx, which comes from the half bridge, and then we have the Vm, which is the voltage over this Lm inductor, or the primary voltage of the ideal transformer, because the transformer is here, right? I will not go through the reason for every single waveform, but I will just show you what they are, and you just have to trust me. So Vx is like this. So it goes from 0 to VDC, and it has a duty cycle of 50%. And Vm is basically the same, just with an offset. So it goes from VDC divided by 2 to minus VDC divided by 2. So with this voltage Vm, we could actually calculate the current going through the inductor, which is Im, because Vm should be equal to L multiplied by the change of Im over the change of time. So you can just rearrange this and find that Im is simply the L, 1 over L, multiplied by the integral of Vm dt. So if we just take the integral, you can see that it first goes down, this is here, and then it goes up, down, up, right? Exactly like this one. And we know for this case that the average value is equal to 0. So it should look like that. And then we have IT, it's more complicated, so you should just trust me that it looks like this. So if I just zoom in, you can see that there is kind of like a dead time there. So it's sinusoidal, and then it goes to 0. Then it's sinusoidal and goes to 0 again. Now we want to find the Ix that you see here. So Ix is simply just equal to the IT plus Im. So it's equal to IT plus Im. So it's just the sum of these two curves. So I just made the waveforms a little bit bigger. So this is the Im, and then this is the IT. Now if we sum them together, we get this Ix. So you can see that the current never goes to 0, or it goes to 0, but that is after it has switched. So this is the current compared with the voltage. So you can see that when the voltage switches over in this point, the current is positive. And then when it switches over again, it's negative, as you see here. It is basically equal to Im. And that is why the current is not 0.